In a previous video, we computed the instantaneous velocity at time t equals 25 of a car traveling with position function s of t equals t squared. Because velocity is the rate of change of position, we might also say that we computed the instantaneous rate of change of the function s at the time t equals 25. The way we computed this instantaneous velocity was by taking the limit of velocities near t equals 25, where the change in time was tending to 0. Specifically, we let the change in time be h, and then we consider the velocity over the interval from 25 to 25 plus h, which was computed to be the quotient of 25 plus h squared minus 25 squared all over h. Taking the limit as h goes to 0, we found that this limit is 50. One way to interpret this number 50 is geometrically. Specifically, on the graph of the position function, the time 25 plus h determines the value 25 plus h squared. This means that the point 25 plus h, 25 plus h squared is on the graph of s. By definition, the average rate of change from t equals 25 to t equals 25 plus h is the change in position over the change in time, which, between these 2 points, is 25 plus h squared minus 25 squared all over h. Notice that this average rate of change is exactly the slope of the secant line connecting the point on the graph at t equals 25 to the point at t equals 25 plus h. Indeed, the slope of this line is the change in y values over the change in x values, which, with these particular numbers, is exactly the average rate of change over this interval. Taking h to be smaller gives another secant line, one which approximates the instantaneous rate of change even better. By taking h smaller and smaller then, these secant lines tend to converge to a line touching the graph at a single point, namely at the point 25, 25 squared. This limiting line is called the tangent line to the graph at the point t equals 25. Its slope, which is the limit of the slopes of the secant lines, is exactly the same limit that we computed when we found the instantaneous velocity. In other words, the slope of this line is the instantaneous velocity, or the instantaneous rate of change of s of t at t equals 25. Because the value of this particular slope is so important, it's given a name, the derivative of s at t equals 25. More generally, the derivative of a function f of x at x equals a is the limit as h goes to 0 of the quotient f of a plus h minus f of a all over h, provided this limit exists. And when the limit does exist, its value, as we discussed, is the slope of the tangent line to the graph of f at the point a, f of a. This limiting value, when it exists, is usually denoted f prime of a, where the prime indicates that a derivative is being taken. The quotient appearing in the limit is called the difference quotient of f at the point x equals a. In general, both the numerator and the denominator of this difference quotient tend to 0 as h goes to 0. But the idea of the derivative is to compare the way in which these quantities tend to 0 by looking at how their ratio behaves in the limit. And when this limit exists, that is, when the difference quotient tends to a finite number, then f is called differentiable at x equals a, and the limiting value is called the derivative of f at a. Let's look at some examples. Here we'd like to compute the derivative of the root function at x equals 1. To do so, we need to compute the limit of the corresponding difference quotient. That is, we need to compute the limit as h goes to 0 of the quantity f of 1 plus h minus f of 1 all over h. Using the definition of f as the root function, we see that this limit is equivalent to the limit of the square root of 1 plus h minus the square root of 1 all over h. The square root of 1 is just 1, so this becomes the limit of the square root of 1 plus h minus 1 all over h. When evaluating limits such as this one, we've seen that multiplying by a conjugate can be useful. Once we've done so, we're able to cancel the common factor of h in both the numerator and the denominator to obtain the limit of 1 over root 1 plus h plus 1. Finally, we've reached a point where we can plug in h equals 0 to get a limiting value of 1/2. This number, 1/2, is the value of the derivative, which, as we've discussed, admits the geometric interpretation as the slope of the tangent line to the graph at the point x equals 1. The point on the graph when x equals 1 has coordinates 1, root 1, or 1, 1. And the line with slope 1/2 passing through this point can be found with the point slope formula to be y minus 1 equals 1/2 x minus 1. Plotting this line against the graph of the square root of x, we do indeed see that this line touches the graph at the point 1, 1, where it appears to approximate the slope of the graph there. As another example, consider the absolute value function. When we try to compute the derivative of this function at x equals 0, we see that we'll run into difficulties. Roughly, this is because the graph has a corner at x equals 0, and so it doesn't have a tangent line there. But let's investigate things carefully using the definition involving the difference quotient. By writing everything out, we see that we get the limit as h goes to 0 of the absolute value of h plus 0 minus the absolute value of 0 all over h. Simplifying a little, this limit becomes the limit of the absolute value of h over h. In a previous video, we actually saw that this limit doesn't exist by investigating the left-hand limit and right-hand limit separately and showing that they don't agree. In particular, the function absolute value of h over h is equal to 1 to the right of 0 and minus 1 to the left of 0, so the right-hand limit is equal to 1 and the left-hand limit is equal to minus 1. This means that the full limit doesn't exist, and so the derivative, which is this full limit, doesn't exist either. In such a situation, we say that the function f is not differentiable at x equals 0. Geometrically, this is evident from the graph, as we said, since the absolute value function clearly doesn't admit a tangent line at the point x equals 0. Indeed, approaching from the right, the slope of the tangent line should be 1, but approaching from the left, it should be minus 1.